Hello and welcome back to the homework help video. This is part 2 on what's this thing called again? I know. This is the practice test. That's what it's called. Words are hard for me sometimes. It's late. It's okay. It's worth it. You guys are worth it. All right, number 18. State the domain and range of this function. This is one that I will be honest, we did not do domain and range just given the equation. We did do domain and range given the graph, but just given the equation. But I included it because I was like, you know what? Even if I don't include a question like this on the actual final, because I don't want to include stuff that we didn't do during the units. It's still a really good question because we could talk about it. So since it is an exponential, we have to know, the graph approximately looks something like that. And therefore, it's got arrows going to the left and to the right. Therefore, the domain is all real numbers, negative infinity to infinity. The range, however, it goes down to this horizontal asymptote, and it goes up from there, and that's it. So that k value tells us the horizontal asymptote, and that also therefore tells us that low point on the range. So -2 to infinity is our range because we have a k value of -2, and the other values, they change the graph, but they don't change the range. So that's the key takeaway from there. Number 19, write the function whose graph is shown. Lots of things going on here. I think the easiest one to point out is the k value. And the horizontal asymptote is normally on the x-axis. It is not in this case. It is down 5 units from there. Therefore, k is -5. Easy. Normally, the reference point is 0, 1. Yeah, that's 0, 1, sorry. And that's because anything to the power of 0 is 1, but the key thing is that it's 1 above the horizontal asymptote. This one's 2 above the horizontal asymptote, and that's why, that's right, we have an a value of 2. And then finally, the last thing is like, all right, well, reference point 1 is 2 above the asymptote. Reference point 2 is 6 above the asymptote, and that actually tells me that my base is going to be 1/3, because one reason I know it's going to be a fraction is because this gets smaller as you increase the power, right? It gets closer to the asymptote and therefore smaller as you increase the power. And power is said to multiply again and again. There's only one way you can multiply again and again and again and get smaller number, and that's if you have a fraction and you're multiplying by a fraction. So that's how I know it's going to be 1/3 as opposed to 3. And again, it's just like 2 over 6. It simplifies to 1 over 3. There we go. That's our whole function. Number 20 is a simplification of some rather nasty stuff. And we can see the steps that I went through. I said, all right, this is a cube root, so I'm looking for perfect cubes, just like that quadratic formula question. I was looking for perfect squares. Cube root of 8 is 2. This cube root of 8 is 2, and the cube root of 5 can't be done, so I'm just going to leave it. How did I know that it was 8 times 8 times 5? Trial and error. I found out what it was divisible by, and I was checking out, perfect cubes. I actually could have chosen a better one. Instead of 8 and 8, I could have said 64. Yeah, 320 is 64 times 5. But anyways, you can do it in parts, in steps like I did. And so yeah, this is 2 times the cube root of 5, because again, cube root of 8 is 2, and I have 2 of them. And that's 4 times the cube root of 5. All right, cool. Well, what about the cube root of x cubed? Well, that's just x. So anyways, you can break it down in parts. Even when we get to like y to the power of 4, well, that's just y to the power of 3 times another y. And so the y, the cube root and the power of 3 cancel for that one. We still have a y that that does not cancel for, and yada yada yada. We see the results here. But again, the key thing is that you can do this in parts. You don't have to do everything all at once. Look at just the numbers, then look at the x's, then look at the y's, and then put it all back together. So there you go. Number 21. We are depositing money into an account. This pays 2.1% annual interest. This is compounded monthly, and so we have a formula for compound interest. We actually had 3 formulas for interest. One was this exact same formula without the n's. It was just 1 plus r to the power of t. That was if it did not say compounding, right? There's another formula that says PE to the RT. I have these backwards, don't I? Yeah, it's not P equals A. I have these backwards. I'll fix this again on the answer key here. I also didn't calculate it. What is wrong with me? Anyways, that's supposed to say A. I forgot to actually plug this in. At this point, I'm like, all right, well, you plug it into the calculator, you get an answer. Whatever answer it says, that's what your answer is going to be. I distinctly remember calculating it. I guess I just forgot to write it. That's okay. Those things happen. You know how to plug into a calculator. And that answer will be posted to Teams, and it'll be on the back of the room and all that. So moving on to number 22, once again we have transformations. This time it's logarithm, and it does the same things. A is a bigger number than 1. It's a stretch. H is opposite. We're shifting right. K is the same. We're shifting up. I don't care the function. It does the same things. Number 23. This one was tricky. These were interesting problems. This was unit 6, I want to say. Logarithms, by the way, unit 7. I think it was 7. So yeah, unit 6 here. Is it 7? Yeah, because 8 was trig. That's right. All right. So unit 6 here. The first way we learn how to deal with these, things with exponents, we're like, all right, well, if I can get them to have, if I could represent them as values with the same base, then I can set their exponents equal to each other. Because if they're the same base, the exponents must also be the same. That's what equals means, is that these things got to be the same. So 9 is 3 squared, and 243 is 3 to the power of 5. I would use easier powers on the test. I don't expect you to know that 243 is 3 to the power of 5. But if you have a suspicion, you can always test it. If I did give you 243 and you didn't know that off the top of your head, you can say, all right, well, 9, that's a power of 3. Maybe 243 is a power of 3, or maybe you try 9 to some power. It's not. 243 is not a power of 9, but it is a power of 3. That's why I chose that one. Cool. Well, the left-hand side already had an exponent, so I distribute it. I get 2x plus 10. And on the other side, I get 5 as my exponents. But again, since these are the same base and they are equal, 2x plus 10 must be equal to 5. So I set my exponents equal to each other, and I solve. X is negative 5 over 2. Number 24, I like this problem. It forces us to use the exponent properties. The logarithm properties. When you have a subtraction of 2 logarithms with the same base, you can just combine them. And the subtraction then turns into a division of, whatever those were logs of, So, yeah, 162 over 6, that's what happened to that subtraction. They combined into 1. You get the idea. 162 over 6 is 27, and log base 3 of 27 is 3, because 3 to the power of 3 is 27. Number 25 was, again, another less common problem for us, but that's fine. The Richter scale tells us that this x sub 0 thing, it just tells us plug in 0.001. Just do it. Just plug it in. So that's what I did. And it says we are looking for a magnitude 9.2. Well, m stands for magnitude, so I plug in 9.2, not in place of x, but in place of the entire left-hand side, in place of m. And therefore, I get these values. Once again, I use a log property here to say, well, this is log of 0.001. Again, then you plug it in the calculator if you don't believe me, but that's negative 3. So we have log x minus negative 3, and that's plus 3. I then subtract 3 from both sides, do 10 to the power of both sides to cancel the logarithm. And it just so happens 10 to the power of 6.2 is approximately that number there. Cool, that's my answer. It is that many millimeters in terms of, how do they phrase it? the seismographic reading in millimeters. So it moves that many millimeters, which is a lot of millimeters. That's over a meter. It's 1.5 meters. So this thing's going crazy. It is like off the charts. It's a very, very large earthquake. 9.2 is one of, if not, yeah, this is actually, we talked about this one before, in fact, in class. This is the largest earthquake ever recorded in the United States. Yeah, I know those things, okay? Just leave me alone, I'm a nerd. Anyways, moving on, number 26. Log base 4 of 1 over, both 26 and 27 are the same. You use change your base formula. This one looks scary because it's got the fraction, but calculators don't care. Yeah, plug in log of, and then it'll say parentheses 1 over, which is just divided by 1024. Make sure you end your parentheses and then divide that by log 4, and you get -5 as your answer. Same thing here, you get 5 over 2. Cool. That's 26 and 27. You just have to know the thing all the way on the right, the value you're trying to find the log of. That's what goes on the numerator. The base goes on the denominator. Quick, easy way to remember that. Base starts with B. Bottom starts with B. The denominator is the number on the bottom. There you go. Cool. Jot that down if you need to, right? So that's 26 and 27. Moving on, I think I can fit everything into just 2 sections here. Okay, moving on, number 28. We are looking at the expanded form of this here guy, and sure, we have a lot of stuff going on here. There is actually one fairly complicated part, and I'll tell you this would be more challenging than what I would ask of you on our final. There's so much going on, I won't expect too many hyper-specifics, more general knowledge things. And anyways, to start, I see a fraction. I'm going to get rid of that fraction. Fractions are divisions. And so I'm going to turn that fraction into 2 different logarithms. And I'm going to put a subtraction between them. So that's a rule that we've already talked about. The rule that is opposite to that is, well, it's 2x to the power 5, 2 times x to the power 5. So divisions turn into subtractions, multiplications turn into additions. Notice how I phrased it. I realized this is actually fairly tricky because it's going to be easy to say without parentheses minus log 3 plus log y to the power of 4. The reason I have this in parentheses is because y to the power of 4, that was on the denominator too, So that should be subtracted in my final statement here because things are in the denominator because they're dividing. So just be careful of stuff like that. Although, again, I don't think I would include this one or one quite like this. Maybe just put one term on the, or one factor, on the denominator rather than 2. So anyways, yeah, we get our last rule here, which is to take our exponents. We can put them out in front and treat them as coefficients. And yeah, cool. So that's the log rules at play. Log 2 plus 5 log x minus log 3 minus 4 log y. The things in the numerator are positive. The things that were in the denominator are negative. There you go. Cool. Number 29 and 30 are very similar. So it gives you the exact same formula, but in number 29, it gives you a time. You just take that time, you plug it in. It says 1 minute. Don't be fooled because this is a function in terms of seconds. So we do have to call that 60. Very important that you know what unit you're working with. And that's why scientists can get so frustrated with us mathematicians. We have a bad habit of just totally ignoring our unit till the end. And it can get us into trouble. But, I prefer to think of it as, I'm so smart. I don't even need to worry about it. I know it's seconds, and you're trying to trick me with a minute. I know a minute is 60 seconds. I just put the 60. It's fine. But yeah. Anyways, just watch out for that. And yeah, you plug into the calculator, you should get around that number, somewhere around there. I'm not going to be super picky on the whole rounding thing. If I am, I'll put it in the question, round to this many decimal points. So like I rounded 2 decimal points here. Other questions I only rounded 1. Some questions I rounded 3. I'm not very consistent with that, mostly because, again, it's kind of the science world that cares about significant figures. And, I probably should more, but, don't let any scientists see this video. We're fine. Number 30. Again, same equation, but this time it tells us a number of millimeters, and that's what S stands for. It stands for size. So we're plugging in for that left-hand side and solving for t. And if you're going to solve for a variable that's in an exponent, you got to use a logarithm. This is log base e that we need, and that's known as ln, stands for natural logarithm, which I know is nl, not ln, but that's because the French named it first, and the French, the way they say it, they say the word with L first. So it's just the way it is. We got to deal with it. And yeah, divide by 0.09 to isolate that t finally, and I get roughly to 102.65 seconds. Something like that. Cool. Number 31, find the exact value of the solution. And I have an argument with this. Oh, okay. Well, I suppose I could just say the exact answer is log base 24 of 12. That's the exact answer, no rounding required. That being said, I kind of prefer, there are cases where I prefer that you actually give the decimal. Is it correct or wrong to do so? Not really either way. I guess it does say exact value, so in this case, perhaps the better answer would be exactly log base 24 of 12. Anyways, I'm getting way ahead of myself. How did I even get that? I need to cancel a base of 24. Logarithms cancel bases. The answers to logarithms are exponents. They leave the exponents. They cancel the bases. Cool. And so you do that to both sides and you get log base 24 of 12. That's our exact answer. That is the approximation as a decimal. Again, I'm just putting that into a change of base. It's log 12 divided by log 24. Cool. Don't forget to end your parentheses when you do that log 12. Otherwise, you're going to get a very different answer. Number 32, solve. Well, we just said logarithms cancel bases, but bases also cancel logarithms. When we put that the left-hand side into an exponent with a base of 3, that cancels the logarithm. Again, we have to do that same base on the other side. We get 3 to the power of 2, which is where I get 9, and then I just solve. I get 1/2. Nice. Number 33, convert to degrees. So we have radians, in other words, and the important thing to know when converting anything is that the thing that you're trying to get rid of goes on the denominator. Denominators divide, and dividing cancels things, So I'm trying to get rid of radians, and that's why I put pi on the denominator. I have had some folks ask, can I put 360 and 2 pi? Absolutely you can. In fact, I encourage it if it makes more sense to you, because 360 is the actual amount of degrees, and 2 pi is the actual amount of radians. It's just us math folks don't like to use unsimplified fractions if we can avoid it. And so that's why I use 180 over pi. So anyways, I divide 180 and 6 by 6, and I end up with 5 and 30. Multiply them together, I get 150 degrees. There is another way to do this. Just look at the unit circle. 5 pi over 6 is on the unit circle, and it matches with 150 degrees. Cool. Number 34, I'm on a Ferris wheel. Fun fact, I've actually never in my life been on a Ferris wheel. Anyways, the diameter is 100 feet and circumference is pi times the diameter, so it's just approximately 314 feet. Our car, is that what they're really called? Sure, our car has traveled 200 feet along this arc, so we've gone 200 out of the 314 total feet, approximately. It's actually ever so slightly more. And that is going to match up with an unknown amount of degrees out of 360 degrees, right? This is how far we've gone out of how far it is in total, and that matches up with how many degrees we've gone divided by how many degrees it is in total. So I multiply both sides by 360 to cancel it, and then I just plug that into the calculator. 360 times 200 divided by 314, and I got approximately 229 degrees. It was like 229.3 or something like that. I can't remember exactly. Somewhere around there. Moving on to number 35. Find the exact value of cosine of 11 pi over 4. I wrote that 11 pi over 4 is greater than 2 pi. The only reason I said that is that means that this is all the way around the circle and then some. So this is actually not on the unit circle. but I can use the coterminal identity, whatever you want to call it. Subtract 2 pi, end up with 3 pi over 4, because again, I want matching denominators here, so 2 pi over 1 is the same as 8 pi over 4, and 11 minus 8 is 3. So I need to find this cosine of 3 pi over 4. I go to the unit circle, 3 pi over 4, aka 135 degrees. So it's in one of those middle thingies where, sine and cosine are the same, but at 135 degrees, it's cosine that's negative, sine is positive. In other words, x is negative, y is positive, and so it's negative root 2 over 2. Number 36, we get one that actually is on the unit circle. Nice. And this is in quadrant 3, so both sine and cosine are negative here. Sine at 7 pi over 6 is negative 1/2. Cosine is negative root 3 over 2. I copied off flip here. I went ahead and canceled the negatives just in my head, and I get 1/2 times 2 over root 3. 2's canceled. You can't leave a fraction with a root in the denominator, so I do multiply both the numerator and the denominator by root 3, and I end up with root 3 over 3. That's the usually given value of tangent at 7 pi over 6. Cool. All right, this is an interesting question. We had a couple of questions like this in our homework. I want to say homework. It was like 1 or 2, maybe 3. I can't remember exactly, but it was pretty early. So we're 175 feet from this tree, and we're looking 20 degrees up. And the important thing is that our eyeballs are 5 feet above the ground. So I need to add that plus 5 at the end, right? And oh yeah, okay, it almost got cut off there. That plus 5 at the end. And so cool. Making this into a triangle, I know the distance, and I want to know this opposite side, how tall the tree is. Well, opposite and adjacent, that's tangent. So tangent of 20 is going to be equal to this unknown opposite side. That's opposite over adjacent. That's the one that I know. Multiply both sides by 175. I went ahead and included this plus 5 in here. Technically, I should have included it in this original equation too. Whatever. And I get 68.7 feet if you include that plus 5 there. Brings us to number 39. We're almost done. Find sine when tangent. This is a very difficult problem. If I include a problem like this, it would just be 1, just for people to give a chance to show off. And it's about knowing, I know tangent. I want to know sine. It says nothing about cosine, so I actually don't want cosine. So this whole part, as I'm taking the definition of tangent, I'm solving it for cosine, because that let me plug into the Pythagorean identity, and now no more cosine. So cosine squared, that's the same as sine squared over tangent squared, and cosine is now, it's gone. So this next step, this is what makes, among other things, what makes it really hard. Well, I have a plus sign here, which means I have 2 terms, and both of those terms have a sine squared. So I can take that guy out, and that's what I do. I factor out that sine squared. That's why it's outside parentheses. Sine squared divided by sine squared. That's where I get the 1. Again, sine squared divided by sine squared. That's why there's 1 on the numerator. And I have tangent squared here. Oh, I just realized I made a mistake on this one. I'll have to fix that. Because I plugged in 1.5, I should have said 1.5 squared. So I will fix this one. 1.5 squared, which is 2.25. So instead of, here, let's not talk about it. I can actually show it on the screen here. 1.5 squared, that's 2.25. 1 divided by 2.25, that's what did I say? Let me try that again. 1 divided by 2.25, and that's 0.444444. And I'll tell you, I actually know that as a fraction because I'm a nerd. That's 4/10. So we have 1 plus 4/10. It gets complicated. 1 plus 4/10, that's actually 16. Did I say 4/10? Come on, man. It's 4/9. 1 plus 4/9 is sorry, I'm losing it, is 16/9. And so, you divide both sides by that, and you copy dot flip, you end up with 9/16. You square root. So rather than this answer, it actually should be the square root of 9/16, and that is 3/4. So yeah, sine should actually be negative 3/4, which is exactly 0.75. So not that far off. Negative because we're in quadrant 3, by the way. All right, so I'll fix that one for the actual thing on the back. Hopefully it made sense, but it is kind of late, so I'm going to have to run with this. 2 more questions to go. And here they are, number 39. Write an equation that describes the graph below. So we have provided points, and that's probably how I'll do it. I'll provide you the points, so you don't have to say multiple answers. Partially, this is a kind of, how shall we put this, selfish? Because if I allow you to put multiple answers, I actually have to think. But if everybody should have the same answer, it's easier for me to grade. So I will most likely provide you points and say, all right, what's the tangent function, if this is the starting point. So if this is our tangent function, this has been shifted left and up. So h is negative 5 pi over 4 because, yeah, that's that point. That's that x value, or theta value, I suppose. And there's our y value. And that's where I get the plus 5 pi over 4, opposites, always opposites, and the plus 1. Why it's negative 3? Well, to get from reference point 1 to 2, we have to go down 3 times. There you go. That's where I get my negative 3. Cool, that's number 39. Likewise, on number 40, I'm told to use these 2 points, meaning we have reference point 1 and reference point 2. I did go ahead and say, well, okay, you could argue that this is reference point 1 and that's going back. I don't know, whatever. So we have a distance of 2, which means our a value, again, since this is sine or cosine, it could be 2 or negative 2, depending on how you think about it. Now, I did say negative 2 for our cosine because, once again, this is below the midline. So sometimes people say, oh, it's going up from there, so therefore it's positive. No. Cosine starts by default above the midline. This one's below the midline, so that's opposite from what normally happens. And that's why I'm saying negative 2 cosine. This has been shifted left, 3 pi over 2. Very, very careful. It's easy to say minus 1 because that point has a y value of negative 1, but it's actually the midline that tells us the k value, so k is positive 1, not negative 1. Likewise, you could say that this is the starting point here, therefore this is sine, and since this starts at the midline going up, it's just like sine normally does, therefore it's positive 2 sine. It's been shifted left pi units, so we're going to say plus pi and then plus 1 because that's where the midline still is. So, ladies and gents, that is all of the questions. Hopefully that helped. I hope you use it wisely. Take very good notes, and I will see you on the day of your final. For the last time, bye-bye.